So you have brain matter in the brain, like the white matter that you see in white and the gray matter that you see in gray. Again, the gray is processing, the white is connecting. And the brain is used for different things. It could be monitoring and setting the function of various organs in your body. And it could be also linked to, or it could be also touch and motion directly. And here you have sight and hearing. So these are a few examples, key examples of what the brain is used for. The cerebellum that you have here also is one significant part of the brain that helps with, for example, coordination and balance. So it directly connects to this brainstem to ensure balance in the body. Obviously, you have certain ways that will connect to this brainstem directly to ensure motion. So in here, I'm not showing the part that takes care of all the organs, but mainly touch and motion. And here, actually, this part of the cortex is directly linked to these functions of motion and touch. You have, for example, your eyes is supposed to be here. It directly connects through some fibers in the white matter to the back of your brain. And this part of the cortex is in charge of sight. And you have another part that is in charge of hearing and will also directly connect to the rest of the brain. So it seems like different parts of the cortex are directly connecting to the associated organs that they're dealing with. This was, and for some huge part of the 20th century, the only picture existing. Like you have a part of the cortex, one part is related to the foot, another part to the hand, and so on and so forth. And the question is, like, is it that simple? And it's pretty sure that it's not, because we are able to solve complex cognitive tasks that there may be something more to that paradigm. So actually, I'm going to take a closer look at how the white matter organizes as a set of axonal bundles or bunch of fibers. So I prepared this small video yesterday. I took 30 minutes to show you a brain. So you see the different parts of the brain with different cuts. So you see, for example, these ventricles are right here, and we saw the cerebellum a bit before right here. So that's the cerebellum, and I'm going to show you the corpus callosum. So it's a huge fiber bundle that can be divided in many different ways, but you can see that it connects right at this middle part in red, bright red. Again, this color coding is for orientation, so red is left to right in your brain. It connects the two hemispheres of your brain. This is one of the main functions of the corpus callosum. So if I go again at it, you see that it fans. I'm going to take out a few of these to show you exactly how it propagates in your two hemispheres, like this. Now I'm going to show you some other thing, the corticospinal tract. So the corticospinal tract is actually made of different parts also. I'm not going to mention them, but you can see that the main point of that tract seems to be joining the brainstem and other parts of your brain. So joining the spine and multiple areas of your brain. So in one part of that corticospinal tract will be in charge of motion, for example. Then the arcuate fasciculus is something that is less known by people, but is in charge of some language tasks and maybe some other things. I am not an expert in this. I just know a few general facts about this, but I know this is one of the tracks. And you can see that it connects different parts of the cortex and just go in green across the brain. The cingulum is another one that we see. I don't remember exactly its function. I'm just trying to show you that you have a bunch of these fiber bundles that are interpenetrating, interconnecting. And this one, for example, I'm going to show it with the corpus callosum that goes around it, literally, like it surrounds this tract. And then one of the last example, I think, is this cerebellar peduncles. There are all these fiber bundles connecting the cerebellum to the rest of the brain or to the brain stem. So all of these are in charge, for example, of coordination and balance and so on and so forth. I'm pretty sure he has other functions I don't know about. But this is also something quite interesting and very well structured. And finally, I wanted to have a few examples of fibers that will propagate from the back of the brain to the front of the brain. And you have this optic radiation, for example, and other ones that I can't remember the name but they were in the video. So all of this, and I put on the side a lot of other fibers that do exist in the brain, but are not shown here. But you just add them together and you have this entire mess of brain connections. And you have a lot of crossing fibers. You have a lot of fibers going, like bending, fanning, and stuff like this. So obviously you have a lot of these that also don't connect one part of the cortex to one specific organ. Like they are part that just connects different parts of the cortex together, and that's it. So this paradigm that I told you before about like connecting the cortex to a certain organ to ensure function is not complete. It needs something else. That gave rise to the field of connectomics. So how to map out these connections in the brain. And this is also called the connectome, like the ensemble of connections in the brain. So connectome comes from genome, is the same suffix. So the field of connectomics started pretty recently, like 15 years ago. And this image comes from the lab I was in Canada. So these guys are experts in this specific field of connectomics. So what is the axonal circuitry of the connectome, of the set of connections connecting different parts of the cortex? That's the question of connectomics. So the application of connectomics, you have a few of them. It could be like studying the brain development or the brain aging. Is these different white matter pathways changing with age? And they definitely do. And also the brain fiber quality will change with development and aging. The brain plasticity is very important when you get some surgery in your brain, for example, or if you have any kind of accident that could happen. Is your brain able to reshape itself to some extent to ensure that some functions will be working on later on? Surgical planning is also one huge part of connectomics, because, for example, you see here you have this brain tumor that has been segmented. And you see that it kind of pushes on the side different fibers. And for example, the corticospinal tract is definitely being shifted and has some part in motor function. So is it affecting the functions or not yet? If you try to resect to get rid of that tumor, are you going to take out some fibers that are actually useful? You want to know this beforehand and maybe try to avoid these fibers. Or if you can't avoid them, you have to tell the patient that there may be a huge risk with this kind of surgery. So this is a very brand young field in surgery, also to use diffusion MRI to get this information before surgery. And then obviously you have the study and monitoring of neurodegenerative diseases. So it could be Parkinson, Alzheimer's, some TBI, like traumatic brain injury, concussions, for example. All of these will give rise to some neurodegeneration in the white matter, for example. So maybe we can find ways to track it and to study also how treatment may be efficient at solving these problems. So you can maybe monitor if certain pathways are getting better using medication. And a last one is also very fundamental. It's like just understanding what's the difference between different animals. Because if you look at all these slices, different animals have very similar brains. They all have some kind of gray matter, some kind of white matter. They all have connections between them. And what are the main differences? Why the human brain seems to have higher cognitive power compared to other brains that may be bigger, for example, the elephant. That's something we're not fully sure about, but maybe connectivity of the brain is the answer.